Most people can calculate an average but have no idea whether that average actually represents the data they are looking at. The mistake is treating a histogram like a bar chart of categories, assuming tall bars are just popular labels rather than intervals of a continuous scale. Mathematically, that means bin choices are distorting the picture, hiding skew in clusters, and forcing data that are lumpy or lopsided to look flat or bell-shaped. You pull up a plot for a deadline, glance at the tallest bar, declare the average is fine, and move on with a plan that quietly ignores long tails, subgroups, and rare but costly events. A histogram slices a numerical axis into adjacent intervals and counts how many observations fall in each slice. Each bar stands for a range, not a single value, and the whole row of bars approximates the distribution, the way the data are spread along the line. The height can represent raw counts, or a rescaled version called density. Either way, the total area of all bars reflects the whole dataset. Unlike a bar chart with separated categories, histogram bars touch because the underlying variable is continuous, or at least ordered along a scale. The shape is not decoration. It is the core message. Peaks point to values or ranges with many observations. Valleys show where data are scarce, and the run of the bars to the left and right tells you about symmetry versus lopsidedness. A histogram is a crude estimator of the probability landscape behind your sample. When you look at it, you are answering questions like, where is the center? How wide is the spread? Which way does it lean? How thick are the tails? And are there multiple clumps that might be different processes mixed together? Take commute times. Most trips cluster in a moderate window when traffic flows, but delays stretch the upper end, so the plot is lopsided to the right. If the center is around 30 minutes, the long string of bars to the right tells you that rare delays are not rare enough to ignore. That shape warns you that a plan based only on the average will underestimate late arrivals because the extra time from long delays adds up faster than early arrivals can subtract. The common beginner mistake is to read each bar as a standalone fact. They point at the tallest bar and say that is the typical value, forgetting that the bar covers a range of values and that neighboring bars might be nearly as high. They see a gap and assume there are no observations in that range, when in reality, the gap could be an artifact of where the bin edges fell. They treat the bars as if they were categories, so they talk themselves into sharp cutoffs and labels that the data never provided. That mistake costs you in practical decisions. You misjudge how risky the extremes are because you imagine that the bulk of the bars guarantees safety. You misread clumps as certainty, so you compress pricing, staffing, or capacity planning too tightly. The correction is simple and strict. Think in ranges, not spikes. When you scan a histogram, always remember that each bar represents an interval. Features are only convincing if they persist under slightly different binning, and the meaning comes from the pattern across bars, not the height of any single one. Bin width is where intuition usually falls apart. Too wide, and you iron out real structure. Too narrow, and you elevate random noise into fake bumps. The actionable move is to experiment with several sensible widths and check which features stay put. Stable peaks and stable skew survive reasonable bin changes. Fragile ripples vanish when you adjust the slicing. Align bin edges with natural measurement units when they exist, but do not let rounded boundaries trick you into seeing gaps or spikes that come from formatting, not from behavior. Now picture setting bins in chunks of 10 minutes for those commute times. That choice will sweep minor rushes and pauses into the same bar, and it may fuse two nearby clumps into a single plateau that looks pleasantly consistent. If you instead used a narrower but still reasonable width, you would see whether rush hour forms a fat shoulder or whether small local peaks represent specific routes or signals. The point is not to chase more and more detail, it is to settle on a width where the main features stabilize and the chatter fades. Skew is the next shape feature to read properly. If the tail runs to the right, big values are more common than the mirror image on the left, and the average gets pulled in that direction. A skewed histogram tells you that the average and the midpoint of the data are not the same thing, and that prediction errors will not balance out nicely. If you plan using the average in a right skewed scenario, you will underestimate how often and how badly you miss on the high side. Modes are the peaks that matter after skew. A single bump suggests one dominant process. Multiple bumps suggest a mixture. In a hiring dataset, for example, a low bump and a high bump in salaries might indicate distinct roles or levels being conflated. If you miss that, you will average across roles, set pay or expectations in the no-person land between groups, and keep wondering why it feels off. Tails are where risk hides, and histograms make them visible in a way tables of averages never do. If about 5% of trips land far to the right, a schedule keyed to the average will fail on you in a steady drip of late arrivals that compound into missed handoffs and overtime. You cannot manage what you refuse to see, and the tail is the fraction you most want to see when the stakes are asymmetric. The histogram shows how thick that fraction is and whether it decays gently or hangs on. The correction for tails is not to trim them away and move on. Use summaries that are less sensitive to the few extremes when you need a typical value, like medians or carefully trimmed means, and keep a separate eye on tail behavior for risk. When the cost of extremes is nonlinear, tailor decisions to that cost, not to the center of the histogram. For operations, that can mean buffers, escalation paths, or capacity slack. For modeling, that can mean loss functions that punish large errors more than small ones. Gaps and spikes often point to the measurement process more than the phenomenon. If you see thin bars at neat rounded values and thick bars just next to them, you may be looking at rounding or reporting habits, not real discontinuities. If bins leave deserted stretches right where a device saturates, or a survey forbids an answer, you have censoring, not absence. Histograms are great detectors of these artifacts. They remind you to ask how the data were recorded before you pretend the shape is natural law. Comparing two groups with histograms is tempting and also treacherous. If the groups differ in size, counting heights will lie to you, because more data means taller bars even if the shapes match. Use rescaled histograms so that areas reflect proportions and keep the bin edges and axes identical across panels, or you will manufacture fake differences. Then read differences in center, spread, and tail shape, not just the position of the tallest bar. Boundaries matter more than they look. Some plotting tools include the left edge and exclude the right, or the other way around, which means a value exactly on a boundary hops between bars when you change widths. That does not change the underlying data, but it changes the look of small features near the cuts. Do not overinterpret crisp cliffs or dents that sit precisely on bin edges. Ask whether they move when you nudge the edges. Transformations are not cosmetic. They let you see structure hiding behind scale. When a variable is positive and spans a wide range, plotting a histogram after a logarithmic transform often reveals regularity that the original scale squashes into a single spike and a long flat tail. After transforming, you can read symmetry, modes, and tail behavior more faithfully. Then translate any decisions back to the original units. Reading shape on the right scale beats forcing the original scale to carry all the visual work. Smoothing overlays, like a gently drawn density curve, can help your eyes connect the tops of bars without getting lost in binning accidents. Use them as a lens, not as a crutch, and ask whether the same bumps appear under reasonable bin widths. If a small blip vanishes when you widen bins slightly, or when you resample in your head, it was probably noise. If a bump persists, it is more likely a real mode worth understanding. A clean workflow is short and disciplined. Start by deciding whether counts or proportions matter for the question at hand. If you care about shape across groups, proportions beat counts. Scan the histogram for center, spread, skew, tails, and modes, and name each feature in words, not hopes. Adjust the bin width within a sensible range and keep only the features that survive the adjustments. Note any artifacts from rounding or censoring, then translate what you see into choices, like robust summaries, segmentation, buffers, or different model assumptions. The next idea after reading shape is position within that shape. A histogram tells you how the mass is laid out. Percentiles and quartiles tell you where a single observation sits relative to the whole. When someone says a score is high or a wait time is terrible, they are really asking what fraction of the distribution lies below it and how far into the tail it falls. The shape you just learned to read explains why those position metrics behave the way they do when the distribution is skewed or multimodal. The shift here is to treat a histogram as an estimate of an underlying distribution, not as a decorative count picture. Once you see ranges instead of spikes and patterns across bins instead of single bars, you stop pretending that an average tells the story. You read skew as a warning about asymmetry and errors, modes as hints of mixtures, tails as visible risk, and binning choices as part of the analysis rather than a throwaway default. That mental model is what prevents you from drawing confident but brittle conclusions from a squint at a single plot. Next, we move to percentiles and quartiles, where you actually stand in any distribution, so you can place any value inside the shape you now know how to read.